Welcome back to Discovering Geometry with Mrs. Berry. This is Lesson 57. Today we will be talking about the converse of the Pythagorean theorem. If we have three measures that fit the Pythagorean theorem equation, will they for certain create a right triangle? Let's find out. So the three numbers that work in the Pythagorean equation are often called Pythagorean triples. So three positive integers that work in the Pythagorean equation. Here are a few sets of Pythagorean triples. The most common is 3, 4, 5, and any multiple of 3, 4, 5, as in we multiply 3 by 2 and get 6, 4 by 2 and get 8, 5 by 2 and get 10. So 6, 8, 10 is a 3, 4, 5 triple just multiplied by 2. There are other triples, of course, like 5, 12, and 13, among others. So our first investigation is the converse true. So select one of the Pythagorean triples from the list. Mark off 4 points, A, B, C, and D, on a string that create 3 consecutive links from your set of triples. In other words, if you had a string this long, you might make a first mark at A and then measure the distance of one Pythagorean triple to B, then the next one to C, and the last one to D. In mine, I chose 5 centimeters, 12 centimeters, and 13 centimeters. Now you're going to put 3 paper clips onto your string and then tie your string from A to D. You will then have 2 marks and the knot that's at A and D. So get a friend to help you and pull the paper clips at point A, B, and C. So at the knot that you tied between A and D and the points B and C. Stretch the string tight. With your paper, check the largest angle. What type of triangle was formed? Go ahead and select another set of triples from the list, get another piece of string, and repeat steps 1 through 4. Here's what it looked like when I did it. I'm measuring my string and marking my lengths. I used 5 centimeters, 12 centimeters, and 13 centimeters. I then put 3 paper clips on my string and tied A to D. I had a little trouble tying my string, so make sure you leave some extra space on the end so that you can tie a knot well. Now I put my paper clip at my 3 markings and I pulled tight. Here's where I had a little trouble. And what type of angle is formed there? That was a right angle, so I did form a right triangle. The converse of the Pythagorean theorem is that if the lengths of the 3 sides of a triangle satisfy the Pythagorean theorem, then the triangle is a right triangle. So yes, the converse is true. So our first example, determine if the triangle is a right triangle. It looks like a right triangle, but as we know in geometry, we need to prove that it is what it looks like. So if it was a right triangle, then we could take a squared, or 13 squared, add it to the other leg of 84 squared, and it would equal the hypotenuse squared, or 86 squared. So we want to know, does it equal? So I like to put a little question mark above my equal sign as I work through the equation to see if it's true. 13 squared is 169. 84 squared is 756. Is that equal to 86 squared, which is 7,396? So 169 plus 7,056 is 7,225, and that is not equal to 7,396. So this is not a right triangle. Example 2. The congruent sides of an isosceles triangle measure 6 centimeters and the base measures 8. What is the area of the triangle? So these are both 6, and this down here is 8. How do we find the area of a triangle? Well, the area is 1/2 base times height. Here we need the height of this triangle. The height is going to be exactly in the middle because this is an isosceles triangle. And when we come down, because it's exactly in the middle, it will form a right angle. In other words, half of that triangle, this base will be 4, and the hypotenuse of it will be 6. This up and down, or the right angle, is going to be h, the height of our big triangle right here. So now we can use the Pythagorean theorem. 4 squared plus h squared equals 6 squared. 16 plus h squared equals 36. I'm going to subtract the 16, and I will get that h squared equals 20. To find out just h, I'm going to take the square root of both sides. H equals the square root of 20. Now, in our algebra review in just a minute, we will remind ourselves that we can reduce this as 2 square roots of 5. And then we come back to our area formula. So the area of this triangle is 1/2 the base of the whole triangle, which is 8 centimeters, times the height, which is 2 square roots of 5 centimeters. Half of 8 is 4, so 4 times 2 square roots of 5, and 4 times 2 is 8 square roots of 5. Centimeters times centimeters is centimeters squared. Now on to our algebra review. We are using radicals often in our Pythagorean theorem work, so we're going to review how to simplify radicals. So if we were to simplify the square root of 75, I'm going to look at 75 and say it is not a perfect square, but what is it? What are some factors of 75? So I know that 75 is the same as 25 times 3. Now 25 is a perfect square, so if this is multiplied inside the radical, we can pull part of it out if we take the square root of it. So the square root of 25 is 5. So now 5 is on the outside of our radical, and inside we only have left that 3 that we couldn't take the square root of. Simplifying the square root of 75 is equal to 5 square roots of 3. What about simplifying the square root of 8,200? Let's take it apart bit by bit. I see that it's even 100, so I know that I could factor it as 82 times 100. Now I look at 82 and say, is there more that I could factor? Well, I can go ahead and just keep going. 82 divided by 2 is 41. Now 41 is not a perfect square, nor can I factor it much more. So I'm going to say that there's no perfect square in here between 2 and 41. But 100 is a perfect square. So I can take the square root of 100 and I get 10. Inside the square root, I'll have the 2 and the 41, which was 82. So simplifying, the square root of 8,200 will be 10 square root of 82. What if I have some things added and subtracted? Well, think of the square root part as a variable, and they have to match to add them together or to subtract them. So this one is 5 square roots of 3, and 6 square roots of 3, and 4 square roots of 5. Well, the square roots of 3 match, so I can add these together. 5 plus 6 is 11 square roots of 3. But the square root of 5 does not match, so I cannot subtract this 11 and 4. This is as simplified as this one gets. 2 square roots of 8 times 3 square roots of 6. When I'm multiplying these radicals, I'm going to multiply what's on the outside together, and then I'm going to multiply what's on the inside together. So 2 times 3 is 6, and inside the square root we have 8 times 6, which is 48. Now I may have just wanted to leave it as 8 times 6 because I'm going to have to take that 48 and see if I can simplify it some more. So 48 is 8 times 6. And now those don't, but we can keep going to the prime factors of 8 and 6 and see which ones are together or common. So 8 is 4 times 2, and 6 is 2 times 3. So now I have 2 times 2, which is a perfect square, and I have 4, which is also a perfect square. If I take them out separately, the square root of 4 is 2, and the square root of 2 times 2 is 4, so the 2 times 2, the square root of that, will also be 2. I still have left this 3 inside the square root. The last thing to do would be to multiply everything on the outside. 6 times 2 is 12, times 2 more is 24. So 24 square roots of 3 is how we would simplify this one.